Hello everyone. So in this video we are going to talk about linear equalization with mean square error criteria. So first of all we should know what is mean by linear, why we should use linear equalization, what is the need. Okay, so in communication channels the signals will be coming with different amplitude and different time delays because the channel will be random and there will be noise in the channel, so the fading of the signal occurs and amplitude and other parameters like phase, frequency will be changing. So in order to compensate those and receive the signal properly at the receiver side, we are using linear equalization. In this we are having two types. The first one is peak distortion criteria and the second one is mean square error criteria. So we are going to talk about mean square error. So in my next video I will be talking about peak distortion criteria. So this is how a general block diagram of a linear equalizer looks like. So it's a transversal filter. It can be called as a filter also. So what we are having here is basically the first one is unequalized input. Okay, so this is the input which we will be receiving from the transmitted. So it will be suppose there is a transmitter here, so it will be passing through a noisy channel here and then it will be coming to receiver receiving part here. So unequalized input means it will be having different amplitude, different time delays, different phases. Okay, so this is the setup which is used to equalize the input and get the correct sequence from the received signal. So z to the power minus 1 means these are the 1 bit delays. So 1 bit delay resistors are those, and these are the filter coefficients or tap coefficients. By suitably adjusting or choosing these coefficients we can equalize the input signal. So here we will be having an algorithm for tap gain adjustment. So to adjust these values, so for each signal these will be different. So to adjust them we will be having some algorithm. Based on that algorithm the calculations will be made, and for this c minus 2, c minus 1, c naught, c1, c2, for those the values will be assigned. So at the end all the samples from each branch will be summed up here and a feedback is taken to correct the algorithm, and finally here we will be getting equalized output which will be nearly equal to the one which we will be transmitting at the transmitter side. Okay, so for this we will be seeing mean square error criteria's derivation today. So in mean square error criteria, the tap coefficients Cj of the equalizer are adjusted to minimize the mean square error value. So as I said, we have to adjust Cj values so as to get minimum mean square error. So Ek means Ik minus Ik cap, where Ik is the information symbol transmitted in the kth signaling interval and Ik cap is the estimate of the symbol at the output of the equalizer. So after equalization we will be getting Ik cap, and this is the transmitted signal at the transmitter. So this is the error signal Ek. Okay, when the information symbols Ik are complex valued, the performation index for the mean square error criteria denoted by J is defined by. So Ik values, if they are complex, then the performance index, that is J value, can be defined as E of epsilon k square. Okay, so this here we are taking magnitude because we don't want negative values here. So E of Ek means Ik minus Ik cap whole square we are taking. So this is the first equation. On the other hand, if the information symbols are real valued, the performance index is simply the square of the real parts of Ek. In either case, the J is a quadratic function of equalizer coefficient Cj. So if they are real valued also, we will be getting a quadratic function. Now our aim is to minimize the value of J in the above equation. So we have to minimize this J value. So there are two cases, infinite length equalizer and finite length equalizer. So we will be discussing infinite length equalizer because there is no such thing that finite length equalizer, because we don't know how many different path signals we will be getting at the receiver side. So generally we should analyze infinite length equalizer. Okay, so first we should find tab coefficients that minimize j when the equalizer has an infinite number of tabs. So in this case the estimate of ik is expressed as, so ik can be expressed as product of ck is, that is cj, and vk minus 1. Vk minus 1 is the unequalized input here. So substitution of equation 2 in the previous one and expansion of results yields a quadratic function of the coefficient Cj. This function can be easily minimized with respect to Cj to yield a set of linear equations for the Cj. Alternatively, the set of linear equations can be obtained by invoking the orthogonality principle in mean square estimation. So we are using orthogonality principle in this case. So which implies E of Ek into Vk minus 1 star equal to 0. L will be lying between minus infinity and plus infinity. So substitute Ek in the above equation. We will be getting the equation where Ik minus j equal to minus infinity to plus infinity Cj into Vk minus 1 into Vk star. So we are substituting for Ek here. So Vk minus L star we are writing as it is. So equivalently we can write this like okay, so take this j equal to minus infinity to plus infinity to the right hand side and write rest of the things as it is. So e into vk minus l star and ik will be multiplied here and written, so this will be taken to this side, so e will be multiplied here, so I have written e. So l will be again between minus infinity and plus infinity here. So to know more over here, to evaluate moments in equation 4, we use expression for Vk given as. So to evaluate the moments, that is coefficients, we are using Vk equal to, this is equation which is derived already. So we are using directly here, n equal to 0 to L Fn into Ik minus n plus neta into k. So that we are using here. So when you substitute that in above equation, E of Vk minus j into Vk minus L star. So these are the real estimated and real value. So this is the real value which will be coming and this is the estimated value. So we are multiplying them both. N equal to 0 to L Fn star into Fn plus L minus j. So this is also same case. Estimated value, this one is star and this is the real value. So these are complex conjugate we can all, and this is the n naught. This n naught means power spectral density of noise in delta Lj, so which will be equal to xl minus j plus n naught delta Lj. So when j is between when the L is less than L minus j, it will, otherwise it will be 0. So in second case this will be equal to f star of minus L when small l is between capital L and 0. If you substitute 5 and 6 in 4 and take the z transform on both sides of the equation, we will be getting like seventh equation, c of z into f of z f star of 1 by z star plus n naught, which is equal to f star of 1 by z star. So the transfer function of the equalizer based on the MSE criteria is, so here c of z is the transfer function, so that is the transfer function of the filter. So that we can write it as, right here it is f star of 1 by z as it is, take this to other side, other right hand side. Okay, so when you take, you will be getting equation 8. Okay, f of z into f star of 1 by z star plus n naught. When the noise whitening filter is incorporated into C of Z, we obtain an equivalent equalizer having a transfer function. So when we apply noise filtering, so noise whitening filter here, we will be getting C dash of Z equal to 1 by f of z into f star of 1 by z plus. So noise filter basically removes the polar part, so that's f star of 1 by z star. Okay, so this I can write it as, because we know that f of z into f star of 1 by z star is x of z. So 1 by x of z plus n naught we will be getting. So the only difference between above expression and the one appear in the peak distortion criteria is the noise spectral density factor, that is n naught. So when n naught is very small, so where n naught is very small in comparison with the signal, the coefficient that minimize the peak distortion T of C are approximately equal to the coefficient that minimize the MSE performation index, that is J. So a measure of the residual intersymbol interference and additive noise is obtained by evaluating the minimum value of J, so denoted by J minimum. So we have to find J minimum here. By virtue of orthogonality conditions given in equation, it follows that J minimum equal to expectation of epsilon k into ik star. Okay, so E of ik square minus j equal to minus infinity to plus infinity Cj into E of vk minus j into ik star I can write from this equation. So this will be equal to 1 because the maximum probability of some function will be 1. So 100% means 1. So 1 minus j equal to minus infinity to plus infinity Cj into f of minus j. This form of equation is not more informative. So more insights will be we will be getting when with the function channel characteristics is obtained when the summation in the above equation is transformed to frequency domain. So when you convert this to frequency domain, we will be getting more insights on this. Okay. So if bk denotes the convolution of these two sequences, the simulation summation in equation 10 is simply equal to b naught. Okay, so since z transform of the sequence bk is b of z equal to c of z into f of z, this is a z transform equation. So f of z I will put here. So c of z I have find out previously, so I will be putting here f of z into f star of 1 by z I will be getting. So this will be x of z divided by x of z plus n naught. So b naught can be given as 1 by 2 pi j contour integral b of z by z into dz. So which you can I can write it as x of z divided by z into x of z plus n naught dz. Okay, so the contour integral in equation 12 can be converted to line integral by substituting z equal to e to the power j omega t. So the result of the change of variable is b naught equal to t by 2 pi minus pi by t to plus pi by t x of e to the power j omega t by x of e to the power j omega 2 plus n naught into d omega. So finally substitute of this result equation 13 for the summation in equation 10. So it's the expression for the minimum MSE in the form j equal to 1 minus t by 2 pi minus pi by t to plus pi by t x of e to the power j omega 2 by x into e to the power j omega t plus n naught d omega. So when you solve further, you will be getting this expression. So t by 2 pi minus pi by t2 plus pi by t n naught divided by t to the power minus 1 n equal to minus infinity to plus infinity h of omega plus 2 pi n by t whole square plus n naught into d omega. So in absence of intersymbol interference, this term will be equal to 1. So hence equation 14 reduces to j minimum equal to n naught by 1 plus n naught. So we observe that j minimum is between 0 and 1. Furthermore, the relationship between the output normalized by the signal energy SNR and j minimum must be gamma infinity. So gamma means SNR, signal to noise ratio, 1 minus j minimum by j minimum. So more importantly, this relationship between output signal to noise ratio and j minimum also holds good when there is a residual intersymbol interference in addition to the noise. So this is how we get the j minimum value in case of mean square error criteria for equalization technique. So if you like the video, please hit the thumb button, and if you are new to the channel, please guys subscribe the channel for more updates. Thank you. Thanks for watching.